This is going to be a bit of a love story. So F# relatively new to me, but we're getting on really well. And I should probably say that while I may occasionally be mean to C#, I'm a big fan of C# as well. I think it's an amazing language that's really come a long way in the last 10 years from what originally started as a bad clone of a crappy Java. And now we have generics and LINQ and all sorts of goodness. So yeah, it's good stuff. Here's the sponsors. You should try to buy stuff from all of these people as much as you can. It's the social contract that you've entered into, so you know. For those who were here last year, I did a talk called Why Functional Programming Matters, and that was sort of part A, and today's part B. So if you weren't here, if you missed that, it was compelling, exciting, and absolutely convincing. And if you were there, then just keep to yourself. But today I'm going to kind of take that as read. So I'm going with the assumption that I've already convinced you that there's some benefit in functional programming, and we're going to have a look at F# and show how we can start to use some of that functional programming goodness in our day-to-day work. Because for me personally, I've decided that F# is what the future should be for .NET programmers. Not necessarily what the future will be, but what I think it should be. I think it's the way for us to level up our performance. So I'll demo some examples of, I guess, hence the things that F# can do that C# can't, right? To show you where the gap is. These guys are Bronze Age metallurgists. They have discovered how to make alloys of copper and to use that to create weapons that they can use to maim other people who are a lot like them. And they did this 3,000 years ago, and at the time they thought they were right out on the cutting edge. This was the forefront of technology. If they had been a little bit more self-aware, they may have thought to themselves that what we're doing here is more art than science. We have trialed and errored, mixing all sorts of things together, and found that some things produce better metals than others. But I think as humanity, we have a tendency to kind of skip that process and just go, hell yeah, I can make bronze, I'm really smart, I can stop learning now. But what actually happened is 3,000 years passed and materials science materials engineering became more of a science and less of an art form. And now we can make cars out of carbon fibre and aluminium chassis, and they go really fast. So this was an art, and this is a science. And the analogy, the very kind of drawn out analogy here, is that I think we're going through this same process, and currently the profession of software development is very much in its Bronze Age, where we're doing trial and error, we're stumbling our way around, we're rediscovering things that we forgot that someone discovered 10 years ago. And it's art with a little bit of science when it should be science with a little bit of art. And I think that there are three vectors basically that we have to move the profession forward. The first one is the kind of people aspect of things. So this is what you hear a lot in the kind of agile stuff. How do we work with people better to get better outcomes? So that's a huge part of it. And then below that sort of people level, we have the systems engineering, what we might call macro architectural issues, which is a large part of what Andrew was just talking about if you were in this room before. And below that again, we have what we could call micro architectural levels. So that's the level of code. And that's kind of the one that I'm going to focus on. At that micro architectural level, how can we introduce more science and have it less kind of random art, have like more defined process to get to the correct solution. And ultimately what I want to do is get rid of bugs. I never want to see another bug in a software program ever again if I can help it. So that's really the principle that's kind of guiding me in my exploration of these topics. One question we have to ask is, does it even matter? And I think the answer is no, to a very large extent. That kind of code level, microarchitectural issues, they kind of don't matter. If you do the sort of work that I do, the problems are all at that top people level. They're all about how do we work out what the right thing to build is, and how do we organize people to build it. If I can make a 5% improvement in the quality of code that I produce or the speed at which I produce it, it's not going to make a lick of difference the vast majority of the time. So 5% is not even really worth thinking about. But on the other hand, if you're doing software for the Mars rover, then a 5% decrease in bugs is worth $100 million. So for those guys, it totally does matter. And the other reason that it could potentially matter is if we're not talking about a 5% improvement, if we're talking about a 20% improvement or a 30% improvement, then it starts to matter again. And I think potentially, if we get it right, we could be looking at those kind of improvements, which is why I care. Which brings us to the question of, how does a C# programmer level up? So there's a good chance that a lot of people in this room, in fact, I know quite a few of these people in this room, have really pushed C# as far as you can kind of push it. Again, like the stuff that we just saw before with Andrew. It's very cool. So once you've done that, once you know C# back and front, how do you make any improvements from that point? How do you put the crayons down? And I think that's probably is the secret, is mastering C# to me seems like becoming an expert in a relatively basic tool. And the next step from there is to look a little bit broader and try to see if there are more advanced tools that we can use to move towards that goal of being scientific and reproducible and so on. And as .NET programmers, the easiest way to do that is to get functional with F#. This is pretty much the only photo I have in this deck that I didn't have to doctor in any way. And there's just no words. In particular, those four gentlemen should probably not be showing anyone their arms. Okay, so let's start really simple and talk about functions. So does anybody know how to write a function in C#? It's a trick question. You can't. C# doesn't have functions. It has methods. The closest thing you can do is you could have static functions on static classes, but there's no way that you can just define a function. And when it comes to doing functional programming, that turns out to be quite annoying, especially because of the stigma around static, and you get lots of code reviews with people saying, stop using static everywhere. But in F#, we can directly create a function without needing namespaces, classes, any other thing. This is what the function definition looks like for a function called square. So in this case, we've got one argument x, and we just square that value. So the square of 3 is 9. Nice and easy. So that's step one, really, where F# comes out of the gate with an immediate advantage that I can just define a function, which is terrific. The next kind of area that I want to talk about is type inference. So C# has type inference, or it didn't originally, it does now. If you have an assignment statement, the value on the right-hand side, if it knows the type of that value, then you don't have to specify the value of the type of the value on the left-hand side, and we have the var keyword where we say, C# compiler, please work the type out for me. But in F#, it basically is a lot more intelligent in the way that it infers types. So you can almost write a program without ever actually specifying a type explicitly, and it would just infer it from the information that came before that point in the program. So for example, in the case of my square function, I've not said what the type of x is, and I've not said what the type returned from that function is going to be. But because when I call it, I give it a float, then that becomes the type that it uses. For example, if I tried to do something like this, I'm calling the square function firstly with a float and then with an integer, and I get a compile error because it goes, you're crazy, that square function wants a float. So it's quite nice not to have to be explicit with types all the time. It makes this a lot nicer to read, whereas the typed version would be float, something like that, and I don't know, it's just not as pretty. I suppose it's not just an aesthetic thing either, it's also the fact that it's just nice to have it work that out for you. Moving on. In F# we can partially apply functions. So this is the idea that you can have a function with, say, 3 arguments and provide only one. So in C# that would obviously be a compile error, but in F# what it does is it binds the first argument that you gave it and it returns you a new function that expects the remaining 2. And that turns out to be quite useful when you want to combine or recombine the same functions in multiple different ways. You'll often need a function with a certain number of arguments. So by partially applying some of them, you can get it to the right shape that you can fit it into a kind of reusable slot. I've got an example for that. So to kind of demonstrate this, I've redefined an add function that adds 2 numbers together. So obviously it has 2 arguments. And from that function, I can provide the first argument, in this case 1. So 1 is then going to be bound to x, and it returns a function that is expecting y, the one remaining parameter. And I've called that function add1, because whatever number you give to it, it's going to return a value that's 1 greater. So here I use the first function, add 2 numbers together. 1 and 3 is 4. Or alternatively, I can use my add function and say add 1, 3, and get the same answer. And that's something that will pop up later. You'll see where, because by itself it seems kind of useless, but you'll see later how that can be a useful thing to have. A sort of somewhat related topic is composition. So where partial application was creating a new function from an existing function, composition is the idea of creating a new function from some set of other functions. So you can combine 2 functions together, you can combine however many functions together as you would like to do. So again, I have the add1 function, and this time I've defined it in terms of F#'s add operator. So it's going to give me a function that'll add 1 to anything. And I've also got my original square function, squares a number. So if I run that, add 1, 15 is 16, square 7 is 49, so it works. Using this composition operator, I can compose the square function and the add1 function. So that's going to create a new function for me called add1 and square. And when you give it a number, say 3, firstly it'll add 1, it'll give you 4, and then it will square that, and the final answer is 16. So we take 2 functions and we make one function that does both of those things. Add 1 and square is 6. So add 1, 6, 7 squared, 49. And a way that you might see someone use something like that is here I'm doing the same thing, composing square and add together. And I'm using the map method to apply that composed function over a range of values from 1 to 10. So for the first value, add 1 and square, 4. Through to 10, add 1 and square, 121. And I should probably point out that this little bit of syntax here, this is a range from 1 to 10, so all the values from 1 to 10 counting up by 1s. That's probably another thing that F# can do that C# can't. So maybe it's 11 things. at least. Okay. Sticking with a similar sort of theme, as well as composing functions, where we take two functions and make a third, we can also use the pipe forward operator. And this is used to create chains of functions. We call one function and take the result, and that becomes the input to the next function. And actually, you've seen this already. I've used it in quite a lot of places. Like, here's a good example. Add one and square, we get the value from that, and then pipe forward into console.writeLine. So that would be equivalent to swapping it around like that. It's the same thing. Or you can do things like this. Same two functions, add one and square. So here I have a sort of pipeline of function application. So we start with 0, so the first add one is going to result in 1, which comes the input to the second one. So 2, 3, 4, then we get to square 4, 16. That's a very common thing that you see in a lot of F# programs, and just creates a nice way to kind of combine function calls together. In a way, it's just a fancy way to avoid parenthesis. You can imagine that the alternative to this would have started with that add one as 0 and wrap that in parenthesis, have add one out the front, wrap that in parenthesis. So people who like Lisp kind of write into that sort of thing, but the rest of us want to not have to count the parenthesis all the time. So pipe forward is quite nice. Tuples, or tuples, and pattern matching. So C#, it does have these, or it has the tuples, but it doesn't have the pattern matching. And without the pattern matching, they're sort of usable, but not wonderful. Because it's easy to create them, it's easy to put values in, but then not so good to get them out again. You have to do the .item1, .item2, so on. So the consequence of that, I think, is that you don't see these a lot in C#, but in F# it's extremely common. So in this example, right at the start here, I'm creating a pair which has two floats. So the first item is the latitude and the second item is the longitude, which is roughly my house. And then there's a function, and the argument to the function is a pair of this form, so float and float. And this pipe syntax is kind of like a switch statement. So we're pattern matching the latitude and longitude pair against these values. So in the first case, we're matching the first item as latitude, and the second item we don't care about, so we just put an underscore. So that's just saying, we know there's going to be something in this position, but we don't care what it is. And I can also constrain that to, in this case, latitudes that are greater than 0. So that's going to output a message telling me that that's in the northern hemisphere, because the latitude is more than 0, you're above the equator. And the second match against that pattern was basically just going to get everything else, because we've filtered out everything that's in the northern hemisphere. We can safely assume that any remaining coordinate is in the southern hemisphere. And the function will then tell me that I'm in the southern hemisphere. And when we run that for my house, it tells me that we're in the southern hemisphere because minus 27 degrees is below the equator. And you can take this destructuring pattern matching a lot further. You can have nested structures of records and tuples and all sorts of things and have them pattern match across. Someone was being smart before saying, is this the talk about CoffeeScript? And CoffeeScript has something kind of similar. So they probably stole it from F#. It was Haskell, but you know, that's neither here nor there. Immutable data structures, again, C# has these. There's a library that you can use, but it's probably more common to see their usage in F#, and it fits with the language a little better. So the idea is that we have lists and arrays and trees and whatever other data structure you'd like to have where you can't change them once you've created them. So they have the semantics of value. And if you want to add an item to your immutable data structure, you just create a new data structure, which is the old one plus the thing that you want to add. And the implementation is quite clever because, say, if I was going to write an immutable data structure, I would do the naive thing where I go, okay, adding an item to my list, I'm going to create a new list that's one bigger than the old one, and then copy all the items across, and that would take forever, and nobody would want to use my data structure. But the ones that are in F# and C# and everywhere else, what they kind of do is keep a pointer to the old one. And so when you add an item, it's just that new item plus a reference to the old one. And it's safe to do that because they're immutable. So we know that nobody's going to change the old collection and therefore invalidate our new one. And what this looks like, boom. Okay, is this kind of thing. So say I start with a list of characters from D through to V. I can then create a longer list by prepending C and then B and then A. So first list looks like that. The second list, I've now prepended ABC, giving me the alphabet through to V. And what we've done here is created a new list from the old list, but the value of list is still the same. So that's what I mean by an immutable data structure. And I can create a third list by taking A through to V and appending onto the end of it another list, which is W through to Z. So W through to Z is one list, my longer list is a second list, and all alpha will be a third list. And they're all immutable, none of them can change or have changed. And that gives me an extremely convoluted way to generate the alphabet. This is nice also for asynchronous type of programming. Again, reminded of what Andrew was just talking about in here. So because we know that these data structures can't change, it's safer to share them between asynchronous bits of code. This is one of my favorite things. So the older I get, the less I like testing. I've sort of come to the conclusion that every test is an admission of failure, especially because the way that we do testing, it's basically poke and check. So you have some program, you poke it with some values, you observe what you get back, and you go, yeah, that looks about right. So clearly on my scale of art to science, this is not a scientific approach at all, or at least it's not a mathematical approach. It's random and haphazard, and it's that old thing about how tests can't show you that a program is correct, they can only show you if it's wrong. If your test fails, you know that it's wrong. If your test passes, you know that it's correct for the particular cases that you looked at. So I don't want to write any tests. And one way that F# can help me with that is via this thing called quick check. So this is a variation on testing. I think of it as a halfway ground between testing and the ultimate awesome compiler that can actually tell me if my program doesn't work. That's what I really want. But in the meantime, I'll take quick check. And what it does, instead of me writing tests, I write properties about my program. So these are invariants, effectively. You say, this program should always have this particular behavior. This is a fact that is true about my program. And I don't have to write the test. Quick check takes those properties and generates a heap of random tests for me and tries to prove me wrong. So in case that doesn't make any sense, code may or may not help. So imagine yet another function that adds two numbers together, and it's got this really weird implementation, and looking at that, I cannot be entirely certain that that's that's logical and going to work. But I've written a couple of tests here. Firstly, adding two positive numbers together, 1 and 3, 4, and adding a positive number and a negative number. 7 and minus 4, 3. So great, I've done my job. I've tested, my function works, everybody's happy. But just for the sake of completeness, I'm going to do a bit of quick checking on that function. And like I said, you do that by defining invariants about your program. And my invariant here is saying that that add function, whatever two numbers I give to my add function, will be equal to what F# thinks the sum of those two numbers is. So basically checking my add function against the built-in one. And then all I have to do is give that function to quick check, and it's generated 100 random applications of that function and gone, yeah, for the 100 that I generated, the property that you've specified is true.
Does it tell you?
Yes, I'm about to show that. Yep. That's cool. Questions are good, man. Questions are good. Lets me know that you're not asleep. Okay, so I've redefined add, so now we have add tick. It's the same as before, but this time I'm taking the absolute value of the first argument before I add them together. So I've intentionally made my add function incorrect. I run my two tests from before, but now with the add tick function. 1 and 3, still 4. 7 minus 4, still 3. So hooray, my tests have proved that my function is still correct. But now we'll quick check. So create a new quick check property, add tick, produce the sum. It's exactly the same as previously, but I'm obviously testing the new add function. And then I give that to quick check. This is a funny thing for a demo because it could potentially generate, I suppose, 100 random inputs that actually do pass, which would be terribly embarrassing. But in this case, it had 9 successful tests before it managed to generate a random input that met my property but failed to, well, I guess it didn't. It violated the invariant that I'd specified, and it tells me what the two functions were. So on the 10th attempt, it used a negative number for the first argument, and because we take an absolute value of that before we add it together, it's got the wrong answer. So this is demonstrating that tests are rubbish.
So does that only really become useful when F# itself can do the test? Like if it's a business logic test for some domain thing, F# can't really sort of validate that test. It's only sort of mathematical ones. Or...
You have to be able to express an invariant, which takes a bit of getting used to. But with practice, I think you find that you can express an awful lot of invariants about domain models. Yeah, it's one of those things that it fits well in this particular topic because I've tried to apply this style in C# and that really doesn't work. It works best with pure functions like the add one that I have here. Because it's just, when you've got IOC and databases and every other thing, it's really hard to create useful invariants. So it's definitely a new way to think about things, and yeah, it takes a bit of getting used to, but I think a lot of people find it quite useful. Yeah. So the last thing I can do, since we're being all F-sharpy, and I didn't like the duplication that I had in some of that stuff around creating properties, I can create a little factory function that can generate properties for me for the various add functions. So this is the example I was referring to before where partial application of functions is being useful. Because you see that make property 4 has 3 arguments. The x and y are the two numbers that we're going to add together, but f is the function that does the adding. So I've dried up my code here because I can call make property 4, provide f, the first argument, and it gives me back a function that expects x and y, the 2 remaining arguments, which I can then just feed straight into quick check. So I can delete a heap of that code that came before, having to do with setting up the properties. And of course, you get the same output. ever so slightly different. I suppose these tests can potentially produce different results every time you run them, which is a bit of a weird thing to think about. But they're still more accurate than the unit testing style.
Can you make it do more?
Yeah, I think you can, yeah. So in some cases, you definitely can. You can also, you can constrain it. So in in that most basic case, what it does is it looks at the types. It goes, okay, those are ints. So I'm going to generate ints. That's the information I've given it. So it's likely that it's sort of in that -2 billion to +2 billion or whatever int range is. But I could also say that my function is add positive numbers, and I could constrain the inputs to say, generate 100 test cases, but only use positive numbers. Yeah.
And if you hadn't called the function before, because you called add one,
Yep.
add tick before you did the quick check,
Yep.
it wouldn't be able to do the type inference.
Um,
No, so yeah, back up a screen. So yeah, so there you can find out.
it knows, it's going to know that it's an integer because of the 0 there. But yes, in general, you're correct. It's not magic. It can't infer the type without sufficient information. And it will tell you that. That's a common compile error. It goes, I can't tell what the type should be. You probably need to add a type annotation. Yep.
I just wondered if it was just start throwing strings and stuff like that.
All right, yeah, yep. I guess it would if we made the function, give it a type variable or something. Yep. Don't ask hard questions, Steve. All right, so one thing I quite like is this algebraic data types stuff. So this is just a slightly different type system to what we have in C#. And there is a video online called Sexy Types, which I quite enjoyed, and the quote is from that. Yeah, they weren't trying to be funny or anything. Like, this is the kind of guys we're talking about. Anyway, Simon Peyton-Jones talked about types and said they're the world's most widely used formal method. And that sounds good to me, because it sounds like we're moving away from ad hoc and towards that kind of scientific stuff that I'm interested in. So algebraic data types are good. And what we mean is we talk about types that can have different shapes. At least that's the way that I think about them. So in C# you define a class and it's got these 5 properties, and that is that type. And it always has to have those 5 properties. But if we have algebraic data types, then we can define a type that looks different in different circumstances. It's kind of like where it's an option. It can look like A, or it can look like B, or it can look like C. So, like for example, here I have a type called point, and a point is representing a point. And so a point can be a point in 2-dimensional space, or a point can be a point in 3-dimensional space. So I have those 2 options for my point type. They have different data, because a 2-dimensional point only needs 2 values, and a 3-dimensional point needs 3 values. But whether I create a 2-dimensional point or a 3-dimensional point, they are both a point. So this is what it looks like to create instances of those types. So I'm creating a 2-dimensional point and a 3-dimensional point. And then I have a function which plots those points for me. So this is my 2-dimensional point. So I think scroll. Oh yeah, okay, so that's plotted the point 3, x value of 3 and y value of 7. And because 2D and 3D are both points, I can reuse my plot function to plot a 3-dimensional point as well, but I've just defined the 2-dimensional plot of a 3D point as being the first 2 numbers. The first 2 numbers that are x and y value. I'm effectively just ignoring the depth component of the 3D point. So it's a nice way to solve that kind of problem. You could, of course, accomplish something similar in C# with, like, say, using interfaces or something. There's always different ways to do the same thing. Don't know what happened to my plot there. Okay, yep, so that's the two-dimensional version of my 3D point. Possibly a better example is this one that I stole from someone else, where we have a recursive type. So that's a type whose definition refers back to itself. And that's a convenient and common way of representing a tree. So I think this is a really nice example of that idea of a type that can be different things, can have different shapes. So we say that a tree has one of two options. It can either be a leaf with a value, or it can be a node which has two further trees. And both of those two things are still a tree. So we can create functions that do stuff to trees, and they'll work regardless of whether they get a node or a leaf or a tree of both of those things. And then creating a tree looks like that. So we have a node at the root level, which has a leaf, and it also has a node, and that node has a leaf and a node, and so on. Lots of nodes, lots of leaves. And, oops. This output here is then just F#, having created that recursive data structure of a tree. This is the sort of default formatting that it gives you that shows the nesting of all those things. Okay. Options. This is one particular data type that you have in F# that people often wish they could use in C#, and I think you actually can. You can somehow reference the F# type in C# and use it that way, but you probably wouldn't get quite the same value because it's not so built in. But you can use it in your own stuff. Anyway, the idea of an option is to, at least a common usage, is to rely less on exceptions, to sort of say, there's one outcome that can happen that I care about, and I'll continue on with my program, and any other outcome that happens, we're just gonna crash because we don't know what to do. So the option is there to represent the fact that some operation could produce a value, or it might not produce a value. So, but we encode that in a type rather than just having exceptions and try catches and the descent into madness. So, imagine I have a function called divide that divides two numbers. You don't even have to imagine because it's right there. And we'll divide 18 by 6 and everyone's happy. But we're all good programmers. Well, I'm sure all you guys are all good programmers. So when I define my function divide as a divided by b, what alarm does that set off in your back of your mind? Like, right, we can't divide by 0, which seems like a bit of a potential bug. And in fact, it's more than a potential bug because in my next example I do it and we actually do get an exception. So if I was a conscientious programmer, I would know that dividing by 0 is not a great idea. So I can put in a test. And I'm going to test the denominator, and if it's 0, I can return a value called none. And this is that option of the option type that says, I can't produce a value for you. If, on the other hand, the denominator is not 0, then I'm going to return the other option of option, which is sum, and it's going to have a value which is numerator on the denominator. So say we do that, we divide 19 by 6. I'm then going to pattern match, much as we did with tuples, on the result. So I can pattern match and say, in the case that the result of that function is none, which in this case means we're dividing by 0, convert that to a string, which is 2 hyphens. But in the case in which it's sum, then convert that number to a string. So 19 divided by 6 is going to fall through this sum option and 2-string that for me. And so we get a numerical value. There are other interesting things you can do with options too, because you have the choice to not immediately unwrap the value. Like that would be the obvious thing to do, right? Call divide, get back this option, and then pull the value out of it. But we don't have to do that. We can leave it in the option wrapper and apply other transformations to it. One way to think of this is if you've ever done any jQuery stuff. So jQuery has a similar kind of concept where you select some elements in the DOM and then you can chain a whole heap of operations to that. And if in your original selection you selected nothing, so you selected some ID or class that's not present in the document, it doesn't cause an error. It just applies your pipeline of operations to an empty collection and doesn't do anything. So we can do that with options as well. And that's what this example is doing. So we're dividing 19 by 6 still, but then using this pipe forward operator and option.bind to send the value of that operation into a function. And in the function, we're multiplying by 2. And then we take that value and do the same thing again into another function. And in this function, we take the square root. So the net effect is that if you have a value, it will go through this process and these sequential steps. And if you don't have a value, it'll do the same thing, but just there won't be a result. So if you didn't have that notion of doing operations on things that are wrapped in options, then you'd have a lot more code because you'd do something, test if it produced a value, get the value, do something, test if it produced a value, get the value, and so on. So this is just a way to avoid that sort of explicit checking. So again, I'm converting the 19 divided by 6 option into a string, pattern matching against none and some, so the same as before. And so this time 2.5 because it's taken 19 divided by 6, multiplied by 2, and then the square root of that, which happens to be 2.52. Andrew was talking this morning about some crazy shenanigans with threads and locks and stuff. Who wants to do that? That's just a way to have bugs, and I want to have less bugs. And there are kind of 3 different concurrency design patterns that I've seen, and that's one of them. That's kind of the C++ kind of locks and threads and very manual process, and don't make a mistake, whatever you do. Oops. Then there's the sort of monadic stuff in Haskell, which really only exists, or at least that's the only place that I've seen it. So that's too complicated for anyone to understand. And the third option is actor model. And the actor model, I think, is sort of popularized by Erlang, which really kind of takes this to heart. And it's the idea that you have concurrency by modeling the independent processes as actors. And actors are kind of like lightweight thread things that communicate with each other via a message queue. They each have their own little queue of messages, and you can send a message to an actor and it will come in on its queue and process it, and it can send messages to other actors and so on. So yeah, Erlang has actors everywhere. Scala has a popular framework called Akka. Go sort of stole the Erlang idea. In Go you have Go routines, which is just, I think you use the word Go and then give it a function, and that function becomes an actor. And Rust has actors as well. So you can do things like, if you wanted to model the communication between people, you could create an actor for every human being on the planet. Think of 6 billion actors running around, and they can all send messages to each other. And that would be heaps of fun. What, is that not your idea of a good time? That's what I do on my weekends, come on. So, this is, I believe, code that I stole. Yep, so this is from Don Syme's blog. Very simple example of an actor. So, yeah, in F# they're called agents. So we create an agent, and the agent is this function here. Inbox is its incoming message queue. And so then we have this while true loop, which is, again, pretty common with actors. They often sit in this closed loop where they're just waiting for messages. So if this actor doesn't get a message, then it just sits there, and when it does get a message, it processes it, and it can do something. In this case, it's writing a message to the console, or it can send messages to other actors. So create one actor and send it a message with the string hello. When it gets a message, it receives it and then writes it to the console. Great, so, hello world with actors. Actors are quite lightweight, which is nice. So in this example, I'm creating 100,000 actors. And the implementation of the actor is very similar. It waits for a message. When it gets a message, it checks if it is the 10,000th or some multiple of 10,000th actor. And if it is, then it writes it. And if it doesn't write it. So instead of getting 100,000, I'm only going to get 10 console outputs from this bit of code. So then I loop over 100,000 agents and send them all a message, ping. Oops, F5. Boom. Okay, so you get, for each multiple of 10,000, you get a message from that particular actor. It's created 100,000 actors, but only 10 of them have any action to do. I'll run that again, because I don't like the output. Come on, you're killing me. The problem is that it's giving me nice, neat, ordered messages. Yeah, no. Not playing well. So the order of these things is not guaranteed, because we're talking about asynchronous actors here. So there's every chance that they'll not report their results in order. But they're just not playing well today. Anyway, so that's 100,000 actors, and heaps faster than the stuff that Andrew was doing with threads and locks and whatever. Monday's going to be tough. Okay, so F# 3 introduced this thing called type providers. I'm pretty sure C# doesn't have them, so it fits in the list of 10 things. The Wikipedia definition's there, so strongly typed access to connected information sources. I think of it as a type provider is a programmed thing that at compile time code gens types for you. So there's lots of community-created type providers for all sorts of interesting things. So you have type providers for web services, you have type providers for CSV files, SQL databases. So take the example of say a CSV file, that's a good example. If you create a type provider for a CSV file and you tell it the CSV file you care about, at compile time, it will scan through the first 1,000 rows of the CSV file, and it will look at, or it will infer the data type of each column, and it will create a type for you with that signature. So then you have strongly typed access to that, to objects that you're going to read from that CSV file, and IntelliSense and all that stuff that people care about. Type provider, cool. Okay, so that's the demo that I'm using here. So I've got movies CSV file is a dump from Rotten Tomatoes of the movie data and ratings per movies. So this is where I set up the CSV type provider on that data set, and then we load that in, look at the first movie in the set, and output the title, the box office score multiplied by 2, the score multiplied by 2 and the box office. So the multiplied by 2 part is in there to show you that it has inferred types, because if it was like a dictionary of strings, which you might get without type providers, then obviously I can't multiply it by 2. So the first one looks like that. The title of the movie is Too Fast, Too Furious. It's not a joke. That's just the first one in the data set. Otherwise, there'd be something in here. Never mind. I don't get in trouble. So the score was 97.8 and the box office was $127 million. And because I like to visualize stuff, we can then take that wonderfully typed data and plot it. So F-sharp's pretty good for that kind of thing too, when you want to do things like statistical type stuff. It's quite clear from this graph, particularly if we were to ignore movies that grossed above $150 million, you can see that there is a clear correlation between the rating the movie received on Rotten Tomatoes and the box office score. So that is what I base my faith on humanity on right there. People apparently do go see good movies. So. Yeah, when a movie is really popular, there's a groupthink effect, and everyone at the cinema just follows everyone else into. It's the best I can do. Titanic.
Terrible movie, lots of money.
Yeah. I think maybe the rating that movies receive changes over time too. People were probably nicer to Titanic at the time, and now they look back on it and it's tacky and the rating goes down. But the box office is the box office. So that was the last of my 10 things that F# can do that C# can't do. Questions?
For that last one, if that file changed, that would...
Yeah.
That was the pathline.
Mm-hmm.
At what time it would fail, give you some message.
If it, yes. So no, don't do that. Yeah, I guess there's limits. It's very clever. It's inferring types based on the data that's there. So if you change the data that's there, it could infer different types, I guess, yeah. I've not actually tried, yeah.
Can you override the inferred type?
Sorry?
Can you override that inference?
No idea. Can you I doubt it. I mean, what would be the point? You might as well not have the type provider, because that's all it does for you is generate the types, so, yeah.
You spoke of a preference for science over art.
Yep.
The core to science is determinism, and your results have got to be repeatable.
Yep.
Does the quick check bother you a bit?
I think that's probably just more a weakness in my metaphor than anything else. It does bother me, but I think it's better than the alternative, which is, repeatable results that we know have big holes in them, because you're only testing a little tiny sample. I guess that's the difference. It's kind of like a broader sample, but more random. Well, it is random where your typical unit tests aren't. I wonder, I imagine you can probably set a seed value so that it is predictable. You can have randomization that's always the same.
I'm sure that's
Yep.
the point. It's going to be predictable. The point is you're not specifying a range, so you're not stating explicitly, I have an expectation when you give this value or range of values, you
Yep, yep.
behave correctly. So if it fails to 7, you could go and run a test for 7.
Yep.
You can't do that, obviously.
Yeah, absolutely. Yep. I can live with that.
Will you make your sample code available online?
I can do, yeah. Yep. I will do. There you go. Yep. And yeah, you should get LinkPad too, because it's my favorite thing in the whole world. Yeah. Yeah. It's just the best. Yeah. Yep.
And the author of which will be here later today.
Okay, good. In which case, I'm very glad that it's not a stolen copy or something. It's just licensed. Trust me. Yep.
Obviously, you're probably going to find it C#, but honestly, is there anything in F# that you wish that's not there, that you wish there was a spiritual successor from C#? So something from C# that you wish was in F# not there.
I think in some ways it's a bit of an unfair question on C#, because there is a lot of kind of parity there. Like most things that, if there's a new awesome feature that goes into C#, it seems to kind of go into F# as well. Does anybody have a C# thing that F#? Yeah.
That doesn't work on F#.
Yeah.
There is an open source plugin that's just not ready.
Also IntelliSense in LinkPad, sadly. Yeah. So you got me there. Yeah, I know.
So
Yeah. Yeah, don't do that. Gotta support people. Yeah, no, I can't think of anything. That's why, I guess that's why I like F#. In some ways, I wish there were things that it couldn't do. It does too much because it's got the kitchen sink in there. You can do functional, you can do objects, you can... It's immutable except for when it isn't. It has no null, which is wonderful because I hate null. But again, it has no null except for when it does.
So how does it handle getting fed a null?
Sorry?
If you got a null back from a database, how does it handle that?
Depends how you query your database, I guess. But it does have a null type. So I think the killer example is base class library functions that return nulls. So because you need access to the base class library, it's going to return you a null, so you get a null. And you just have to understand that it can occur and be sad. That's all? Okay, thanks guys.